Hi, and today we're going to be looking at the first part of wave characteristics. And today's lesson pretty much finishes up our basic understanding of traveling waves. We're going to be looking at a number of different issues. We're going to be looking at wave fronts. What is a wave front and what does it represent? We're going to be defining, the intensity of a wave. We're going to relate this intensity to amplitude, which you should remember is a feature of a wave. And we will then relate intensity to distance from source. So we're looking at some definitions and two basic mathematical relationships. Now, if we consider a traveling wave, which we looked at previously, it has certain definite sections. Here you can see how circular amplitudes can be visible throughout the water. What you're looking at there are the crest and the trough of a wave. You're seeing the top of the amplitude drift along, and the dark circles represent the lowest part of the wave, which is a trough or a trough. It's spelt trough, but it's pronounced trough. This diagram shows you the wave image, and you can see here quite visibly that there are areas where the amplitude shows a depth. It goes from the center down, and that would be your trough, and where the amplitude goes up to the highest point, and that's called a crest. Now, a wave front is basically the motion of the crests as the wave is progressing. Here we can see in a three-dimensional model of what that looks like. We see here in red the wave crests moving through space. Those are our wave fronts. The diagram below is a two-dimensional representation where the wave crests are light, our wave fronts are visible in green, and our troughs are dark blue, and they represent the lowest point of the wave. So this shows us the progression of the wave through space by looking at the points of maximum displacement, the crests. Now, these wave fronts are very, very specific in their behavior. The wave front represents the wave direction. The distance between wavelengths would be the distance between wave fronts would be equal to one wavelength. Of course, because from a crest to a crest, we have an entire wave. And the actual direction of the wave is always perpendicular to this wave front. So in complex situations where you have to draw diagrams of wave fronts, it's important always to notice that that wave direction is perpendicular to the wave front. Okay, so these diagrams show explicitly the wave direction is this way, the wave fronts herein. We'll use the grey to maintain this consistent approach. The wave fronts are perpendicular here. The wave direction is this way, and the wave fronts are perpendicular. There is a special case, which is the radial wave front, where this perpendicular behavior gives you a circular wave front, or what we call a radial pattern. Right? This is your typical water droplet situation. Why is the wavefront circular? Well, the wave direction is in all directions away from the source. And so therefore, the wave fronts, to compensate for this variation in motion, create this circular pattern. So a radial wavefront is circular because the motion is perpendicular to the wavefront direction. Here's a simple question. You can stop the video and have a think. The diagram below shows a wave, a water wave in a ripple tank. Which line represents the wavefront? So stop if you need to think, or just wait and you'll hear the answer. The answer is B. And if you were asked to consider where the wave direction is, you would say that it's in this direction at 90 degrees to it. So moving this way. It could be moving this way as well, as long as you get the direction right. Okay, so that's the first objective. What is a wavefront? We're now going to look at amplitude and intensity. So far we've talked about a number of different aspects of waves, but we haven't mentioned energy. Now, energy, as you should remember, is a scalar. It's a quantity which defines the potential to do something. Energy comes into waves via the concept of intensity. Intensity, by definition, is power per unit area. Now, power, you should remember from topic 2, is energy per second. So, the definition of intensity is the energy per second per square meter. In classical wave theory, the energy or the intensity of a wave is directly related to its amplitude. So we're not going to consider wavelength and frequency in this section. We're going to focus mainly on amplitude. Amplitude being the distance from zero displacement to maximum or minimum displacement. The relationship is a square relationship. As you double the amplitude, the intensity is 4 times greater, because intensity is proportional to amplitude squared. This has interesting connotations, particularly in nature. For example, tsunamis, waves which have the potential to cause mass devastation. One of the issues with tsunamis is that as they approach the shore, their amplitude increases. This is a behavior that's affected by the shore line decreasing, or the depth decreasing. As that amplitude increases, the intensity of the wave increases, but by a square relationship. So the actual energy of the wave is massive by the time it actually breaks. The second relationship we're going to look at is an inverse square relationship. It's also to do with intensity, the power per unit area, but this time we're going to consider the distance from the source. If you have a source of light, you get closer to the source, the brightness increases. This is something that we're all familiar with. It's fairly obvious. The closer you are to a source of light, the stronger that light is. Well, actually, that relates to its intensity. The brighter it is, means that there is an equivalent increase in intensity. There is more energy per second per square meter. Now, we could relate that to our amplitude relationship. In fact, as you get closer to a light, you can see that its amplitude increases. As a light spreads out from its source, that amplitude basically distributes its energy over a wider area. And so therefore, the amplitude decreases over distance. And so therefore, the relationship, or the equivalent relationship in terms of distance, is an inverse square one. Intensity is proportional to 1 over distance squared. If you double the distance, the intensity goes down by a quarter. So those are our 2 relationships. Now, both of those relationships can be dealt with mathematically by considering proportionality. If intensity is proportional to amplitude squared, then intensity, or if you want to write it as an equation rather than a relationship, then intensity is equal to a constant value times amplitude squared. What is this constant value? Well, that depends on the source of light. It depends on the wave that you're considering. So this is not a number that you need to worry about, as it will change from question to question. But if we take this relationship and we express it now in terms of the constant, what you have is an equation which is like this. The intensity divided by the amplitude squared will give you a constant. This should remind you a little bit of the gas laws, where you had these proportional relationships that you manipulated to then look at changes in one of them. Similarly, intensity is proportional to 1 over displacement, or distance, squared. If we equate that, then you would end up with intensity equals constant divided by x squared. And so therefore, by rearranging, we would end up with intensity times distance squared equals constant. This allows you to have a bit of fun with situations where waves are changing their amplitude in order to make predictions about their intensity. Here's a question you can try now. Look at the following pieces of data. Are y and x squared inversely proportional? That means, does y equal 1, or constant, over x squared? Is y equal to k over x squared? See if you can figure it out. And of course, stop the video and try it before you check the answer. So, if y is proportional to 1 over x squared, then x squared times y should give you a constant value. And what you should find is that when you try this with x squared times y, x squared times y, you will not get the same constant value. A relationship that's proportional would give you a constant value always. Example from my assignment sheet. Ocean waves coming onto a beach have an amplitude of 2 meters and an average power of 5.2 times 10 to the 4 watts for every meter of their length. Estimate the power per meter which would be transferred if their amplitude was reduced to 1.3 meters. To gas law questions, you're given 2 conditions before and you're being asked to consider what will happen later. The amplitude is 2, the power is 5.2 times 10 to the 4. Amplitude and intensity have a relationship which is equivalent to intensity is proportional to amplitude squared. So what constant does that give you? Intensity over amplitude squared would give you a constant, which is then equal to the new situation when the amplitude is reduced to 1.3. So the intensity over the amplitude squared before is going to be equal to the intensity over the amplitude squared in the new situation. So you use this relationship. Have a go at the questions, work through my solutions, and let me know if you have any specific questions that you want me to go over in another video tutorial.